Okay, so this is lecture number 4. So we'll continue uh, our discussion from the last time, and there were some observations to start with, which are easy to show. So we were talking about linear independence. So this is obvious. Any reordering of a linearly independent we'll abbreviate by Li set is also linearly independent. That's pretty obvious. If V1, V2, V3, Vn is linearly independent, then of course V1, V3, V2, any sort of a reordering is also linearly independent. Second, consider a non-zero vector, a single non-zero vector V1 is non-zero. This is V1 is linearly independent. And finally, consider two vectors and the ordered set V1, comma V2. So these are linearly independent. When are they going to be linearly independent? So one thing is sure that if they are linearly independent, then so it's an if and only if condition. You can verify it. If either of them is zero, well, of course, that's anyways a statement of linear independence. Or you have V1 is a multiple of V2. So in that case, they are linearly independent. So what else? Now we come to the definition of what is a basis. So consider a set of vectors in V, V1, V2, Vn, which is linearly independent. That's the first condition. Second, they span the vector space. So if these two conditions are met, a set of vectors which is linearly independent and it spans the vector space, this is a basis. So we'll denote basis by B. And every vector belonging to the vector space can be expressed as a linear combination of elements of V. So I'll have for any vector for any W belong to vector space, I have this expression, And not only that, this is unique. How do we show uniqueness? Well, consider another linear combination, and these are equal vectors. This was our original linear combination. Now, subtracting, I have C1 minus C1 prime V1, C2 minus C2 prime V2 equals to 0. And I have C1, C1 prime, C2, C2 prime. This implies, so this means that all the coefficients are equal, so we have a unique way. So that's a nice useful concept of a basis. Basis usually need not be an orthonormal basis. We certainly can have the orthonormal standard basis which we deal with for a vector space. This is called as E, where I have E1, E2, En, and they're just going to be your column vectors. This is E1, E2 is going to be, E3 is going to be, so on and so forth. So that's called as the standard basis, which we typically use. So now we are going to write down a few propositions. The proofs are in the book. We'll briefly discuss how to go about them. But so what's the proposition? Let me just number the page. And the proposition is the following: L be a linearly independent set. LV, just an addition of another vector to L, is linearly independent if and only if V is not in the subspace spanned by L. So that essentially is the idea. V should not be in the subspace spanned by L, and then LV is a linearly independent set. So how do we go about showing this? Well, you can consider this set, what I can call as L prime, you can consider this to be linearly dependent, and then you can proceed from here. So that can be certainly one of the ideas. So say your L was V1, V2, VR, and consider if V belongs to the span of L, well then V can be expressed as a linear combination like this, and then we have a linear relation. We have C1 V1 plus C2 V2 CR VR minus V equals to 0. So that means L prime is linearly dependent. Uh, Conversely, you can show that if L prime is linearly dependent, what does it mean? It means the same thing. This condition holds, if L prime is linearly dependent. Uh, well, we can argue that B is not equals to 0, because if B was equals to 0, I have another linear relation. B equals to 0 implies this, and we know that this uh, cannot be true because we started with L being a linearly independent set. Hence, this is not true. Hence, B is not equals to 0. And what I can do now is that I can express V in terms of the other vectors. So thus, V is in the span of L. So if I start with L prime being linearly dependent, then it necessarily applies that my vector V is in the span of L. And if I start with these guys being linearly dependent, then I can necessarily show that well, if I can show, if I can say that V is in the span of L, then I can also show linear dependence. So my proposition is that I can only extend the linearly independent set as long as the vector I find V is not in the subspace spanned by L. So that's the bottom line. It's really easy to show these things yourself also. I urge you to read these proofs from the book as well. So what's my next proposition? My next proposition is, consider the set then the span of S is equals to span of S prime. Uh, Here S and S prime are ordered set of vectors and related by this sort of an expression, S prime is S comma V. Then the span of S is equals to span of S prime if and only if V belongs to the span of S. Well, the proof is this proposition is very similar to the previous one. That's the idea. And you can easily show it. We won't go through the proof of this. The proof is in the book over here. So, with that, I come to a definition. Definition is that a vector space is called finite dimensional if there is a finite set S that spans V. So this is my definition. Uh, I have a finite dimensional vector space. If I have a finite set S that spans V, and for next lecture or until unless specified, we are going to be dealing with the finite dimensional vector spaces. So what's the proposition? Any finite set S which spans V contains a basis. So in particular, any finite dimensional vector space has a basis. So how do we go about proving this? Well, since I have a set S which spans V, uh, then what do? I can write it down a linear relation like this, where I don't have all of these guys to be C1, C2 till Cn to be 0. So that means I can solve for Vn, and Vn gives me I'm assuming that at least one of them is not 0. Let's say this guy is not 0, so I can write it down as this guy's. So this shows that Vn can be written in terms of these guys. So what I'll do, I'm going to remove Vn from my set. So my set is going to be now the modified set. Modified set is now going to be V1, V2, Vn minus 1. And notice I still span the vector space because the vector Vn was anyways we were able to write it in terms of the remaining vectors. Uh, so this way I proceed to eliminate all the vectors which were causing an issue with my linear independence condition, yet retain the span, and finally I'll get a subset, maybe n minus k, that is going to be linearly independent, as well as it's going to span the vector space. Okay, so we are going to state another proposition. You can read it from the book itself. It's called 3.15. Let V be a finite dimensional vector space any linearly independent set L can be extended by adding elements to get a basis. Well, so the idea is simple. You start with the uh, some L, pick a vector V which was not in the span of L, add L to V to create another guy. Now repeat this process. Now you'll have another vector V prime which is such that V prime is not in the span of L prime. Then you get another thing which is L double prime, which is going to be L V V prime. This way continue till you get a basis. Okay, so as a last proposition, which is actually uh, kind of hard to prove, uh, the proposition is the following, that let S and L be finite subsets of V, assume S spans V, the vector space, and the fact that L is linearly independent. Then we need to show, or the proposition is that then S, the set S contains at least as many elements as L. So that's the idea. And so how do we go about showing it? I have a set S, let me repeat it, that spans V. It need not be linearly independent. And I have a set L that is linearly independent, but that need not span the vector space V. I need to show that the set S contains at least as many elements as L does. So once again, we are going to use the fact that if I have n equations, or I have m equations in n unknowns where n is greater than m, then this guy has a non-trivial solution. So how do we use such a result and combine it with the two of the conditions given to get what, to prove what we need, that the set S contains at least as many elements as L. So the idea is the following, that well, let S consists of vectors and L has vectors some Wn. Now I can always express any element Wj of the set L through a linear combination of vectors from S, because this guy spans this, this spans the vector space V. So span of S is equals to V. So I express, I just write down my linear combination over here. Now consider another vector u, which is a linear relation of the vectors of L. So this is a linear combination, which I can write it down as this guy. Now I substitute each w from this equation and I get this guy. So see the coefficient. So what is the coefficient of each vi? It is this guy over here. So it's a sum j times, that's the coefficient. Now if this coefficient is 0 for every I, well then u is equals to 0. So essentially to find a linear relation among vectors of L, it suffices to solve this sort of an equation, and this is an equation between m equations and n unknowns. Notice what was m? M was the number of elements in this set, my set S, and n was the number of elements in L. So if m is less than L, then this has a non-trivial solution, which implies this has a non-trivial solution, and hence the vectors, therefore the vectors in L are linearly dependent. So it better be true that m is at least equal to n, if not greater than n. So that's how we show the proposition over here. Some trivial corollaries of this thing you can read from the book is that two basis sets, which we call B1 and B2, that means these guys span the vector space and are linearly independent of a vector space, have the same number of elements. Okay, finally, I mean, it's really easy to show. Just think about it a bit and you can actually read it from the book as well. Finally, we come to the definition. Essentially is that the definition of the dimension of a finite dimensional vector space V is the number of vectors in a basis. So the dimension will be denoted by dimension V. Okay, so finally, the last part of this lecture, I have the proposition which says that if S spans V, then S is greater than dimension of V, and equality holds only if S is a basis. It's really easy to show. In fact, it follows from what we just proved. And if L is linearly independent, then L is less than equal to dimension of V, and equality holds only if equality holds only if L is a basis. Okay, so we'll end up here. There's another proposition 3.20. You can read it from the book, or maybe we can do it the next time. But next time we'll start with the computation with basis, change of basis, so on and so forth. Thank you.